All right, how are we doing, everybody? Pain? Yeah, I know, we just went over the exam. Anyways, today we're just going to go over Laplace transforms again. This time we're going to do inverse Laplace transforms, which is very important. Let me see if I got my notes. We're going to go over the computer assignment tonight, assignment 5, all right? Maybe we'll even do it. Let's see, full bit by bit. I'm going to do it brick by brick. Inverse Laplace transforms. Let's see. Basically, we just said, hey, we got a Laplace transform, right? We did stuff with it, right? And then let me see. Transformation that maps a Laplace transform into an impulse response, okay? So here it is. Here's just the notion. We want this, right? So all we do is just, this is the symbol, okay? That's how we memorize it. Easy. You guys took Math 432? Is that where they taught it? Or 431? Okay, that's good. Null function, he says, if it's defined by that, don't worry too hard. Let's see what else. I want to go over some. Yeah, that's funny. Anyways, I have it backwards. Inverse Laplace. Yay, not inversed. See, he goes over examples. The Laplace transform is two signals that differ by a null function. No, I don't want to do that. Ew. Inverse Laplace transform using tables. So he just says, hey, you're given this Laplace transform, or some guy hands you out this card. If there's a table, right? Remember this table right here, right? That table of all those, what do you call it, properties? This right here? Or is that properties? No, that's the wrong one. I'll show you guys later. If you just memorize this, right, you can technically work backwards. Like, okay, I don't know the inverse Laplace transform, but I do know this, so I'm just going to work backwards. Boom, done. Is that easy enough to understand? Do you guys understand what I'm trying to do there? No? All right, this is what you guys are going to do on your exam. Okay. Get title page, EE360. What do you call it? Inverse Laplace transforms. Today is November 12, 2025, page 1. Whew. Anyways, so you have your best friend right here, S plus A, correct? So Dr. Suber says, how does it react? I don't know. What does it do? I don't know what it does in real life. Does this make any sense to you guys, what this looks like in real life? No? So you guys remember that Laplace transform table, right? Where which was this right here, this rule right here. Remember that guy right there? So I'm like, hey, I don't remember. I don't know how to do this crazy integral right here, right? There's an integral, and it's painful. I don't want you guys doing it. So you got to memorize the tables. But I know that, hey, it's going to be in the general form of, I don't know, some constant e to the, what do you call it? A of t, u of t, right? You guys know that guy, that signal, right? Is that correct? So if our A is equal to minus, what did we say? Minus 2, minus 4, plus 4? Yeah, it's going to be minus 4. Minus 4. Right, that's good. And then, well, our constant right here is just 1, right? Then you can basically solve this for, okay, x of t or whatever is going to equal to e to the minus 4t. U of t. Congratulations, you know how to translate poles into the real world. Is there anyone clicking on why I'm saying this? This is the most fundamental thing that you have to memorize for the rest of your life. So if you were given this Laplace transform, right? Here's imaginary s, right? And real of s, correct? And I just said the pole is going to be at s minus 4. So this is 1 over s minus 4, correct? So that means s has to equal 4, right? S has to equal 4. To make this cancel out, is that correct? Wait, hold on. If S is equal to 4, pole at 4. Is this right? I don't like this. Hold up. Because you know this function right here, right? If t goes to infinity, right? What is this going to look like in the time domain? Here's 1, right? Or what do you call it? X of t. Here's time, right? It's going to look like this. Right? It's just going to go down. Does that make sense? So what I was trying to say, let me see. Maybe I got this wrong. Shouldn't be wrong. S plus 4. Oh, I'm dumb. There we go. I forgot the plus sign. S plus 4, okay? That's why I was joking. S is equal to minus 4, okay? So we have a pole at S minus 4, right? S is equal to minus 4, right? So it's going to look like this, right? And now draw the ROC, right? What's our region of convergence? Right-sided, right? Is it causal?
Yes.
Yes. Why? It's right-sided, correct? Is it stable? Yeah, it goes down to 0 at infinity, right? T is equal to infinity, correct? It's stable, right? It goes down to, it settles, right? It's just a pulse. So is it stable? Come on, you're killing me. Yes. Why? Because we include the entire imaginary axis, all right? Our signal stable, it's causal, LTI. LTI system, linear time invariant. So yeah, get this fundamental in your head because you're going to get to the point where you're going to see this in your exam. And we're going to go over, hopefully, a problem on that if we have time. Where if you're not H of S, let's see, yeah, let's whatever. It's going to be, what do you call it? A S plus, I don't know, A1 plus B S plus A2 or whatever, right? Is that good? And I say, can you realize this function? What is this going to look like? What's the impulse response? Oh, that's easy, Dave. It's going to be this. H of t is equal to estimating A e to the, what do you call it? A1t plus B e to the A2t, right? Don't forget the U of t. I don't know why he forgot it, but don't forget that, okay? Promise me, okay? That's your answer. That's going to be your final exam, or that final exam 5 final problem. Memorize that, okay? Is this making sense with everybody, okay? You're going to memorize this, all right? Or some form of this, okay? So if you can go from this to this, you're done, all right? There's another hint I'll tell you guys. This right here is considered the residue. There's a residue, okay? And this right here is the pole, okay? And then let's just say I multiply this whole equation, correct, by some constant k. This right here would be your gain. All right? So then you get RPK, for those who play Call of Duty. Anyways, residues, poles, gain. All right? That's what you guys are also going to be seeing in your exam, or what do you call it? Computer assignment 5, okay? Is that making sense where these are coming from? So let's just say if I were, that's why I wanted to show you guys an example. I want to show you guys a MATLAB example. I was trying to show you guys this. Let's see, S real. I don't want to do this. S imaginary. Give me a plane. Great. SZ. I'll show you guys later tonight. The point is, you're going to get to the point where if I drew this in 3D, right? And if I were to have a pole right here, like let's just say this right here is M, right? We're looking like this. Here's real, right? And the poles are all on our left side. If I were to draw this invisible box, right? Here's our invisible plane. If our poles were right here, you're going to see these tents, and it looks pretty cool. And I can't draw this in 3D, but you'll see these poles. And if you take an integral of all these poles that exist on this plane, like if it exists right there, right? You can realize this and say, hey, all you got to do is just look at the residue, of that pole. You're going to see different styles of poles. If I were to look at it from, let me do another way. Here's the real axis, okay? And here's value, okay? I'm not looking at the imaginary axis, okay? This is how you do it. So if you're probably going to see some function that's going to look like this. It's going to go into infinity. But you'll realize some infinities are bigger than other infinities, okay? Does that make sense? This is, what do you call it? A view from this side. If I were to look like this, if I were to look from this angle, okay? I'm just looking, or not this. I'm just looking at just this axis, okay? The real axis. Does that make sense with everybody? So I'm going to look at these poles, right? And this is my left plane. Or wait, no, not left plane. Yeah, left side. And this is my right side. Right, GHT, correct? Does that make sense? Let me do it again from a top view, okay? I'm going to do top view. If I were to look from top right here, it's just going to look like this, okay? I'm going to call this one S is equal to, what do you call it, -4. S is equal to -2, correct? -4, -2. Is that making sense? Is what I'm showing you right here? If I were to draw your region of convergence, correct? ROC, right? Is it stable? Yeah? Because we include this imaginary axis? Yes? And is it causal? Because it's right-sided? So that means this is a stable system, okay? You'll get some general equation that's going to look like this. Some, I don't know, residue 1 e to the, what do you call it, -4 plus residue 2 e to the -2t u of t. Is that making sense with everybody? What I'm trying to show you guys? Are you guys understanding how to read this plot? This is a very important tool, okay? You guys, that's why the MATLAB is important too. I think this one should be more straightforward on how to actually achieve it. We'll do that later tonight. But this right here is our Laplace transform from a top view, okay? This is our imaginary. This is our real, right? You guys are familiar with that, okay? ROC is good. You know that these two are poles, correct? Our system's stable and causal, correct? This right here is just a 3D representation, okay? There's another pole out here. It's just whatever. And this is from a side view. I'm just looking at a slice just on this axis, okay? You'll see that in your assignment tonight, all right? Is that fair with everybody? Any questions about that? Anyways, let's keep going. So yeah, now that's there. So then you got all these other inverse Laplace transforms. Oh, you're given this. You just got to memorize that table, okay? This one, is this going to blow up? I don't think it will. Will it? S has to be less than or equal to 2. Oh, this one's going to blow up. Yeah, it's going to blow up. Inverse Laplace transform using properties. You have your addition property. You know the Laplace transform of two systems is just the Laplace transform of the individual ones. Is that good with everybody? Let's see, inverse Laplace transform, tables. Here's a sinusoid. I think that's what it's looking like. Yeah, sinusoid. Why did I say sinusoid? So you're going to see things that are going to trigger you. And anytime you see an S squared on the bottom, it's going to be a sinusoid. It's going to be a resonator. Okay? You guys build resonators in labs? No? Inductor and capacitor, resonator, tank circuits. Anyways, let's see. Partial fraction expansion, heavy side, okay? This is the one I need you guys to memorize, okay? So you're going to realize you're going to have these like complex Laplace transforms, right? But you can separate them into just these, well, just regular S's and then partial fractions, okay? You see? So he gives you this toughie, okay? And I think he's going to give you this on the exam. I'm not saying it's this problem, okay? You do the division, okay? Okay, what's this? Do your partial fraction expansion division. divide this top part by this bottom part, right? Everyone know how to do long division, correct? You get to the point where it's this, okay? What's the Laplace transform? Inverse Laplace transform is 6s. Let me grab that. Laplace. Where is our table? I don't like memorizing. Is this it? No, where's our thing? There you go. I hate memorizing. Let me see. S? Where's S? S of n, f of s, right? If S is 1, right? Let me show you this. 6s, right? Well, that one's just 1, so I don't think that's going to work. Never mind. It's not going to work as I wanted it to. Anyways. So you're going to get this equation right here, right? This is what you actually have to do partial fraction expansion. So let me see if he shows you that right here. Simple method with simple poles. Okay. He just says, oh, this ugly equation right here can be turned into poles. Okay? Let me see what else is there, because I want to get to state space equations. Rationale of poles. Okay, here's one. So basically, if you wanted to find the residue of a pole, right? If I went back to our example, right? And I want this pole right here, this s equals 2 pole. I want that residue. Some infinities are bigger than other infinities, correct? So I want this pole, right? So, okay, if I want that pole, just multiply your, your transfer function, right? By that pole, okay? So now the pole's gone. And now you got to solve for the value at that pole. Is that making sense, or should we go over an example? Go over example, Dave. Come on, waste our time. Or use our time, I don't know. Heaviside cover-up method. Yeah, literally this right here. You see this pole right there? He says, here's your pole. I want this residue. Multiply that by that pole, and boom, you realize that that pole is gone. Now you just can solve for your equation. So it becomes something very easy. It's called the Heaviside cover-up method. All right, let's see. How does he do this right here? Okay, so he says this has to turn into this, okay? And I don't like these numbers. Why did he give you a hard example? He should have made something easier. I don't like that. Go back up. Here's your pole, right? Let me just explain it. I don't like this. Okay. Because people like visualization. I like pictures. Okay, so don't worry. I'll write this. Alpha 1 or residue 1 of s plus 2. Don't worry, I'll write this. I'm hearing the yelling. F of s, A2s plus 2j plus A3s minus 2j, okay? All right, engineers. I'm giving you a pole, all right? Painful, all right? So this is all equal to, let me just go back to our painful equation, 4s squared plus 6s plus 4, right? And then s plus 2, s plus 2j, s minus 2j. There you go. Right? So this nasty equation, right, can be generalized as this, okay? And now here's where the pretty pictures come to play, right? So we know we have a pole at s is equal to minus 2, right? So I'm just gonna do this. Boom, done, right? Easy, correct? I have one at 2j, right? 2j and minus 2j, right? Pole right there, right? So then if I wanted to find these integrals, right, I know if I just circle these guys, right? If there's going to be a residue, right? So let's just say I want this one right here, okay? I just want that one, right? S is equal to minus 2, correct? So all I got to do is just take this fat equation. If I want residue A of S is equal to minus 2, correct? It's going to equal, just multiply by S, what do you call it? S plus 2, right? Times this whole ugly equation. 4s squared plus 6s plus 4 all over s plus 2. You're going to do this in your exam, by the way. S plus 2j, j2, s minus 2j, right? Is that good? Then you realize that these two cancel out, dot, 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 like that. And then you got to solve for this when s is equal to minus 2. All right? So that if we put minus 2 into this is going to blow up. Right? Is that good with everyone? It's going to blow up. But now that we got rid of that pole, now we don't have to worry about things blowing up. Right? Now, anyways, let's do this painful math. What's 4s squared? Okay, got 4 times, who wants me to rush through this? 4 plus minus 20, no. 6 times 2 is minus 12. There we go. Plus 4, right? Now I lost that pole, so all I got to do is minus 2 plus j2, and then minus 2 minus j2, all right? Now I just got to solve for my constants, okay? So do I want to do this? Let's do 16 minus 12 plus 4. Uh-oh. I don't like this. Did I mess something up? What's 16 minus 12 plus 4? Well, actually, no. We're fine. It's okay. 16 minus 12 gives you 4, and then that gives you 8. There you go. Then if I do this complex conjugate multiplication, let's see. Minus 2 and minus 2 gives me 4, right? And I do this 4. This gives me positive j4. This right here gives me minus j4. And then this right here gives me minus another j4. No. J squared and j squared gives me that. It's going to be minus j squared 4. Is that good? Which is equal to, these cancel out. 8 over 4 plus 4. Is everyone good with that? What's the residue of that pole? 1, right? So if I wanted to, we just solved for this, correct? So if I wanted to estimate f of t, right? Boom, we got our first pole where a1 is equal to 1, right? So that means we can just guess. E to the minus 2t u of t. Boom, answer to that part. Now you got to do it to the other two. Is that making sense? You see how much work this is going to be? That's the heavy side equation, okay? Anyways, let's keep going because there's a lot of math here. Oh yeah, boom, done. Boom, done. Solve for the same thing too, okay? Let me just move this down here. Partial using this, just another problem. Solve the problems, yada, yada, yada. Partial fraction, using other methods. What? What's he making you do? He's just doing the same problem over and over again. You guys like that? No, man. 145, 143. Partial fraction expansion with real coefficients, conjugate poles. Yeah, this is a bunch of reading. Did you guys give you videos to watch? Anyways, let's go over this. Quadratic partial expansion. Let's see if this is important. Oh, this one's important, y'all. Okay. Ooh. Man. Okay, you'll notice that sometimes you're gonna get a double pole. Let me see if this is what it is. How does he know that you have a double pole here? You're gonna realize something here, because this is your pole, right? But then you get this equation, And you get to the point where if you do have like two poles or something like that, you're gonna have to guess again. Put this S right here and put that there. It gets ugly. I don't like it. Where does he start that? Because I don't like this. I want you guys being prepared. Quadratic. Let me give you guys some pointers. Okay, this is the rule right here. It starts right here. I don't know how to explain it to y'all, but basically, if you see a point where you have quadratic equations like this, s squared minus whatever here, you gotta have to use this, okay? So there's a Shams outline homework on that. Good luck. Anyways, not too bad. You have a square right there. Yeah, this is gonna be painful, y'all. And you have, let's see, I want to keep going. Trigonometrics, partial fraction expansion with repeated poles. Okay, now this is the other one too. Double pole. Okay. Repeated poles. Oh, man, do you guys like this hieroglyphics? I don't. Let's see what he says. What does he do here? Partial fraction expansion. You find this. You have a triple pole right here, right? So if you have the case where you're given a triple pole or n pole, right? You guys like this one right here, this first pole, A1, SO plus 2, right? Easy homework, right? Now here's the hard part. You have to do this 3 times. 1, 2, 3, okay? Memorize that, okay? For second order. I think you might do second order. I don't know. Double poles, okay? So once you do that, you can solve for these just by multiplying this guy right here by that. A1, A2. How do you solve for A3? To determine A3, substitute A1 and A2. What the heck? What incarnation did he do here? You have to solve, okay, you basically punch these two in, you put it on the other side. What? You put it on the other side, you combine this, and then you get this mess right here. Oh, God. That one's going to be a toughie, y'all. Anyways, I don't think he's going to go that tough. Ew, look at that. Anyways, let's see. What's next? Heavy side cover-up, because I want to solve this using the heavy side function. I don't want to... There we go. All right, this is what you guys got to memorize. So don't do the first part. Do this second part right here. You're going to do derivatives. You're going to forget this, okay? Let me see. You have a single pole right here, right? You have a triple pole here, a double pole here, and a single pole here. So for this triple pole, right, all you got to do, or wait, let me see. The single pole right here, right? You just do the same thing. You do what you guys are hardwired to do, okay? This triple pole right here, easy, okay? You're just doing something simple. A1 and A2 are easy, okay? Now this is where it gets hard. A3, right? I want this, but we have a double pole. When our max, we have a triple pole right here, right? Triple, double, single pole, right? So for this one, you need to take one derivative of this. Or derivative of the whole thing. Is that what he's making you do? I don't know. I don't like this. Let's see. Let's see how he did this. We got to prove his math. He tells me, David, you're going to take over my textbook when I die. I'm like, what? Am I going to get your royalties? No. Anyways, A3, right? This is the puppy that's going to hurt you on the exam, correct? Is equal to d of ds of s plus 1, 3, right? We're doing a first derivative, correct? F of s. What was f of s equal to? Where's that nasty equation? Right there. D of ds s plus 1 squared or cubed times s plus 1, 3, s plus 2. So I'm wondering if you can multiply this out by just canceling this guy right here and canceling this guy right there to give you, let me see if this is what he does, ds of 1 over s plus 2, right? Which is equal to, who knows how to do this, ds s plus 2 to the minus 1. So that gives you, the power goes down, right? Well, let me see. Let's see if Dave remembers the chain rule. You get s plus 2, right? That one right there, right? Is that correct? And then you got to take a derivative of whatever is in here, which is just 1. Did I get that answer right? Is that what he did? Let's see. Yeah, there it is. Oh, but there's a minus. Because I got to multiply this guy right here when I do my, what do you call it? My power rule. I got to put a minus right there, okay? Don't forget that one. He's going to penalize you, I think. All right? Now you got to evaluate this for s is equal to, what did he make you evaluate? Minus 1 over minus 1 plus 2 squared. Or was the whole thing squared? I think the whole thing is squared. No, just the pole was squared right here. Which is going to give you minus 1 over 1. Is that good? Is that painful? Yes. For A4, right, which is a single pole, okay? It's a single pole, but it's established it's already been a triple pole, right? You got to do 2 derivatives of this whole thing, okay? That's painful. So, yeah, just memorize those 2 equations. The heavy side for your simple poles and your repeated poles, okay? Now let me see if I can go over other things, because I think Dr. Stuber, I'll have to tell him to cover the state space equations. Yeah, that's pretty much it right there. So pretty much it. It's just memorizing the tables and getting to partial fraction expansion. That's all this class is. Once you start realizing how easy this is in terms of, what do you call it? Getting to, let me see, this point right here, we can finally start analyzing these poles. Your exam is going to be, I gave you some transfer response, right? Transfer function. Now turn it back into the time domain, okay? Is that good with everybody? Let's see if there's any last minute things I got to show you. Let me see, inverse Laplace. By the way, is anyone noticing that today is MATLAB Day? Yeah, it's National MATLAB Day. They're doing presentations all day, so I think they have an AI class today or something like that. Let me see what else. LTI. So if he goes over this, let me just tell you one last thing before we wrap up. Let me see. Yeah, I want to talk about this because I'm not so sure how he's going to do it, but I want to get you guys ready. This is the LTI packet. This is the last of the packets that I gave out last week. Oh yeah, here's how you do your state space equations. Let me give you an answer. Here it is. Is this it? There you go. You guys remember these little puppies? Yeah, you guys hate them or love them. I don't know. You can turn this into a Laplace transform. When you have a derivative, right? What happens when you have a dyt, right? Convert that to Laplace. What happens? You get S, Q of S, right? And then that initial condition, right? Which is annoying, okay? You get this, you get this. You just convert everything to Laplace, okay? Then you realize you can, what do you call it? You have this Q right here and this Q, right? Bring this one to the other side, you get this, okay? Memorize this location, okay? It's not going to be on the exam, or maybe it will. Okay? Initial condition, right? Input, right? ZSR, ZI, or ZIR, ZSR, right? Solve this equation, boom. Boom, that's your answer. Everyone's going to memorize this one? I'm just giving you guys a hint. Okay? And that's pretty much it. And then, yeah, you get your response. Oh, here's the other thing. He says, if you recall, you can find your impulse response looking at this, right? Boom, and then he just ignores that. ZSR, done, go home. Anyways, that's pretty much it, what I can show you guys. We went over heavy side stuff.
Yeah, we'll have discussion today. We'll go over the assignment. Make sure you guys are up and running with that so you can study for your exam, which is next Wednesday, right? Next Wednesday, I called him and told me that. I'll keep the format to where the assignment is due that night too. I don't think we'll have discussion next week then. Other than that, are there any other final questions? No? All right, y'all. Have a good day.